A long time ago, there was a famous traveler traveling the world. He lived in a country. The country was called the Water Kingdom. He lived in the Water Kingdom. And someone told him there's this amazing place. It's called the Fire Kingdom. And someone gave him a map of the Fire Kingdom. But it was not a map of the way to the Fire Kingdom. It was not a map of the way to the Fire Kingdom, unfortunately. It was just a map of the Fire Kingdom itself. He set out, find a Fire Kingdom. Our traveler. He went out around asking, have you seen this country? Someone said no. Have you seen this country? Someone said no. Someone said it's that way. Someone said it's that way. He went around traveling. He went all over the world. One day, he reached the Fire Kingdom. And it was amazing. It was so unique. It was so different. And it fit the map perfectly. It must have been the Fire Kingdom. Till he realized that he was actually back where he started. The Fire Kingdom was his hometown, the Water Kingdom. He looked at the map carefully. It was the same map as his hometown, drawn in a different orientation. Sometimes when you see everything is new, maybe the things haven't changed. You are looking at it differently. Let's go back to spirals. We have been discussing these special signal shapes, which I call spirals, okay? Which, by the way, now I can tell you the official name for the spirals. They are called the Fourier basis, okay? Search for that name, you'll find the spirals. I like to give it a geometric name, so I'm calling it spirals. But I didn't invent the theory. It's called Fourier basis, okay? So, they are a special geometric shape which is complex numbers going around in a spiral, literally, right? And that spiral is going to have a particular angular frequency or angular speed, correct? It will turn some angle per sample. Yes? So, if one of the values is 1, then the next value will be 1 at an angle of omega, and then 1 at an angle of 2 omega, and here you will have 1 at an angle of minus omega, 1 at an angle of minus 2 omega, and so forth, okay? And the very intriguing fact about this is that because of the very specific nature of how complex numbers work and how complex multiplication works, these spirals are a complex geometric series, correct? Or a complex geometric progression, okay? What we studied was all geometric progressions are eigenvectors of all convolutions, any convolution, okay? And so, in particular, these spirals of any omega are an eigenvector of any convolution. Yes? And so, whatever convolution you may have, with whatever convolution rule you may have, the output is going to be a spiral rotating at the same omega. It may have a different size and may have a different angle with respect to this spiral, but it is going to be a spiral rotating at the same omega. Okay? What that also means is that the output is a scale of the input, is a complex scale of the input, right? Because a size and a turn are both representable as a single complex number multiplication. Correct? We saw a real consequence of this, right? This is complex numbers, so this is happening in some abstract mathematical game world. But a real consequence of this that we saw was that any convolution will always transform sinusoidal sine waves into output sine waves of the same frequency. But the sine wave could be of a different amplitude and it could be shifted. So it could have a different phase with respect to the input sine wave. Correct? In general, if you think of a linear function or a linear operation, let us say A, okay? And let us say that A has two eigenvectors. Let's say X and Y are two eigenvectors. And X becomes alpha X when operated upon by A, and Y becomes something, let's say beta Y when operated upon by A. If I gave you this much information, what are the vectors for which you will be able to quickly calculate what A does? Any linear combination of X and Y. That much is clear to you, right? So Ax plus By, you will be able to quickly calculate what is the output to that just by using linearity laws. And what will be the output? The output is going to be A alpha X plus B beta Y. Correct? Now, does that mean that any input any input to A could be analyzed, can now be analyzed? That's not necessarily the case. Okay. But can you imagine a situation whereby such an eigenvector analysis actually allows us to analyze any input to the linear operator using just eigenvectors? Yes. So one thing that would be useful is if X and Y are independent. What does that mean? X and Y are not scales of each other. They are like in two different directions is what it means. When you have just two vectors, it's easy to see. And that will mean that Ax plus By will span a plane. But that plane need not be all the possible inputs to A.
So if the dimension that you're looking at and the number of eigenvectors for which you have the information, if you have d unique eigenvectors, then that's sufficient. D unique, by unique I mean they're independent of each other.
Right, correct. So the intuition here is, yes, very nice. The intuition here is that if you are in a d-dimensional space and you got a set of d eigenvectors such that none of them is a linear combination of any of the others, then you will be able to reach any vector in that space as a linear combination of these vectors. Okay. Now this is a particular theorem in linear algebra called the rank nullity theorem, which I am not going to prove right now. If you remember it, you remember it. Basically, a d-dimensional space is always spanned by d independent vectors. There's a theorem like this. Okay. So, I have a nice three lecture mini series on it. It's not on the web, but it will be one day, and you can see the videos are already recorded. So it's very nice. You can look it up. Rank nullity theorem. Okay. So, but we'll just try to imagine this using our geometric intuition that if you have a plane, you'll need two vectors to span it, correct? One vector will never be enough, and three vectors will always be too much. And two vectors will be right. And you can imagine various sets of two vectors working to reach that entire plane. If you have a three-dimensional space like this, three vectors going in different directions will be enough so that their linear combination goes anywhere in this space. Correct? So, if an eigenvector set could be found which are all in a different directions, independent, and there are as many eigenvectors as there are dimensions in your space, then you will be able to analyze any input A using this methodology. Is that clear? Okay. And so the question we ask ourselves is that, is this set of eigenvectors that we have found, it's a rather large set of eigenvectors because every omega gives you a distinct eigenvector. Is this large set of eigenvectors enough to analyze any convolution entirely? Which means that, do these eigenvectors span the space of all possible inputs? Okay. At least intuitively you understand this. I know formally it's a bit heavy, but okay. Questions? Huh? Not the answer. The question is the question intuitively understood.
Even possible to answer this.
Why do you ask that?
I'm just thinking like from a computer science perspective. Like I'm thinking about it that if I had the data and I wanted to verify that these set of eigenvectors are possible for any convolution, how will I go on verifying it? Because there can be infinite number of convolutions that are possible, correct? So how do I go on checking about this? That's something that was coming.
Yeah. That's a good point. And we'll see what we'll see a version of the answer. And yeah. That's a good point, and that is why actually Fourier analysis, to me at least, is immensely surprising that such a theory exists which manages to do all of this in such a beautiful fashion for such an important class of operations is not trivial. And the reason I am teaching it in this fashion rather than in the fashion of, hey, here are the schemas, you switch them around, is so that you see that, oh, something rather exciting and surprising is happening inside. Okay. We are going to switch our point of view a little bit. Eventually, we'll try to address this question. Okay. We are going to discuss periodic signals. Till now, we have not mentioned this at all, or as yet at least. So, yes?
Secretly, we have been discussing them, right? If you really look at that.
Do you think these are periodic signals?
I mean, you turn enough, you reach
Depends.
back.
Depends on what?
That's it. Divisible by 360 divides like 1
No,
turn
but
divides.
any angle 360 times we rotate will eventually turn.
Yeah, yeah. But what if the angle was root tooth of a turn? Then it's very periodic like, but not actually periodic if you look at it. So there are, among these eigenvectors or among these signals, spiral signals, are signals which are rotating and coming back on the circle, but still not actually hitting the same value again ever. This could happen. Okay. So, right. If omega is any rational number in turn units, half a turn, 1.5 a turn, quarter a turn, 3/8 a turn, it's periodic signal. Okay. Because then there is some time in the future where it completes a turn or an integer number of turns, which means it's back where it started. But there are others as well, which are not periodic. Okay. Okay. Sorry, we just jumped ahead a bit. What is a periodic signal? A periodic signal is a signal with a period, which basically means a signal which repeats its own values periodically. Is that okay? Right? So, for example, if I say an 8 periodic signal, that will be let's say these are the values, and then after 8 samples, the 9th sample is again going to be this sample, and then it will continue repeating the values exactly. Okay. Then again a third time the same thing will happen, and again the same thing will happen, and so forth. Okay. The same thing is happening to the left as well. So a periodic signal is periodic in all directions. So this same thing is happening to the left as well. Okay. Is this clear? That is a periodic signal with a period of 8. You could have a periodic signal with a period of anything specific. We are imagining the periodic signal to have this period repetition all throughout that axis. Okay. Like from minus infinity to plus infinity, it is repeating those same values. Now you will say this is impractical, and it is impractical, right? Because it cannot have any real world meaning, right? A signal which has always existed and will always exist, that is periodically doing the exact same thing again and again. Some people think the universe is that way. Okay. Both some religions as well as some physicists think the universe is that way, but periodic. But leaving that apart, in our time windows, we never see like an infinitely periodic thing. So it's an idealization of something, and we'll not worry about the philosophical meaning of the periodic signal at the moment. Okay. Any questions? Someone was saying something here, but you're okay, no? No. Suppose I have a periodic signal and I am going to let's say I have some convolution rule that I want to apply to this periodic signal. Can you tell me something interesting? The output will also be periodic. What's the proof?
The convolution would be linear combination of the original signal but shifted.
Okay.
And each of them is periodic.
Yeah, you can just mechanistically see. It's like intuitively obvious that it will be periodic. But pressed for a proof in the formal fashion, the easiest way to prove it is to say that if I shift the input by exactly one period, then by shift invariance, the output will have to shift by one period. But shifting the input by one period does what to the input? Nothing. The input remains as it is because that's the meaning of periodicity, right? And so the output shifting by one period should also be doing nothing to the output, which means the output is also periodic. Get that? Right. And so the output is also going to be an 8 periodic signal if the input is an 8 periodic signal. Which means that it is possible to gain a knowledge about the entire output in a finite amount of computation. It is
every element of the signal, you just need the finite elements in that set.
Which is another way to put it. Yes, basically that if you knew the outputs for any one period window, then you know all the outputs. So if you calculate the outputs in a 1 period window, then you know all the outputs, correct? Right. So, I mean, imagine this. So 3, 4, 5, 6, 7, 8. This is a 1 period window in the output, correct? If I calculated these 8 outputs, then by periodicity, I will know the entire signal because it's the same outputs being repeated all throughout time, all throughout history and future. The same thing is happening again and again, correct? Can you say something similar about the input as well?
Yes, the exact reverse. With this, you can reverse convolve get the input. So, same thing.
No, forget reverse convolving. No. That's
Even like it's periodic, right? So the values keep repeating.
yes.
So even if you know a small segment, you can just say for the entire part.
Yes. So if I knew the input for just one period, sorry, I will be able to calculate the input for the entire input. At this point, we are going to do a switch of our mental model. Okay, this is an 8 periodic signal, correct? This is an 8 periodic signal. And let's say real signal. Forget complex numbers for the moment. Real signal. 8 periodic signal with real values. What is the dimensionality of the space that this signal lies in? Hmm? 8 to infinity. Wait. Ask a side question in a moment. He wants to go on a side quest.
Unique values, which are like number of linearly independent vector values.
Do you see that you can imagine the 8 periodic signal, the mathematical structure of an 8 periodic signal to be an 8-dimensional vector space, because you need 8 numbers to describe it. Okay, what are its 8 unit vectors?
8 values. 8 values. The period.
No, what are the actual unit vectors is the question. And linear combinations of those 8 unit vectors will give all 8 periodic signals.
N plus t values of the actual sequence, where n is the 8 plus t, where t is the natural number. So each unit vector would be
So 1 at whatever positions he told and 0 otherwise.
Oh, okay. Again, yes, your collaboration. I just failed to realize without say it again.
the first unit vector would represent all the values at time 1, time 9, time 17.
So what is the unit vector? So what he's saying is a better variant of what you're saying. Okay, here's one unit vector. 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1 0. That's one unit vector. Why? Because the vector itself has to be 8 periodic, right? Because it has to be in the space of 8 periodic signals. So all zeros, 1 and all zeros is not an allowed vector anymore. It's not in this vector space of 8 periodic signals. Okay? So one of your unit vectors is 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1 0 0 0 0. What's another unit vector? 0 1 0 0 0 0 0 0 0 1 0 0 0 0 0. Okay? You get the idea? How many unit vectors are there? 8 of them. And linear combinations of these 8 vectors get you any 8 periodic signal. Do you understand this? And that's how it's an 8-dimensional vector space, because a linear combination of 8 vectors gets you anywhere in this vector space. Does it make sense? Write this.
No, but I mean, the thing is, whenever we're talking about complex signals,
And no, we are talking about real signals right now.
I mean, is it that the diagram kind of assumes we are talking about real signals, right?
Yes.
That was, oh.
And so I said real number, just think of real number. I said that. I made sure I said that. This is not complex signals. We'll have to get there, and we'll have to confuse ourselves with that in a moment, but not now. Is this okay? So yes, the 8 periodic signal is represented by 8 numbers. That is true. And it's these 8 numbers, right? I mean, whatever they are. Maybe it's 3, minus 2, minus 3, minus 2, 2, minus 1, 4, 1. Maybe those are the 8 numbers. These 8 numbers are representing this 8 periodic signal. So they are 8 numbers. So just if you think about how many numbers did you remembered a list of 8 numbers. So in that sense, in this fashion, it looks exactly the same. 3, whatever, right? 8 numbers, one after the other. But in your mind, you are remembering that it means something different. It is representing 8 periodic signals, not say whatever other, not something else. Okay. Now my next question is, so 8 periodic input signals, 8 periodic output signals are both now represented as a bunch of numbers, 8 input numbers, 8 output numbers. Can you reimagine the convolution as an operation that applies to those 8 input numbers and produces 8 output numbers.
Just a clarification. So when we are convolving a signal with another signal, the signal which we are the spreading rule, it has finite non-zero numbers and the rest of them are zero. Or
For the time being, let us say it has 3 non-zero numbers, the way I have drawn here. Let's leave out the generalization for a minute later. The problems are going to occur, you're right. Let's leave that out and let's just say I have 3 non-zero numbers the way I have drawn for simplicity, okay? So I have that convolution. Do you understand the problem? The convolution physically is happening just the way it was happening. But since the entire information of the input signal can be compressed into 8 numbers, and the entire information of the output signal can be also compressed into 8 numbers, the convolution must have a representation from 8 numbers to 8 numbers. And the question is, what is that representation? What is that function that will take 8 numbers, do something, and produce 8 numbers? Three numbers as a row. You have to flip them to make them a row, okay? And then 8 of them.
It's like I'm thinking about it like matrix multiplication. It won't violate the rules.
If it is a matrix, it is a what times what matrix? It is an 8 by 8 matrix. If it is a matrix. Is it a matrix?
It's linear copy.
Yeah, the question is it linear in this description space? And it is, I'm going to say something slightly difficult. The map from the description space to the actual periodic signal space is itself a linear map, which means that the representation of the linear function is actually going to be a linear function in the description space as well. I said something difficult. If this didn't map, it's okay. Okay. Yes, they are going to be. It's going to be a matrix. It's going to be a linear function from 8 numbers to 8 numbers, and you'll see that that's mechanically the case. So this abstract nonsense that I just said, you don't need it. So basically, imagine this convolution is going from just 8 numbers to 8 numbers. How does it look like? That's the question. See, like a Toeplitz matrix, kind of. Okay, let's. Okay. How is this output produced? Let's just look at some output and let's try to see what happens. How is this output produced? You take this input, multiply it by some number here, right? You take this input, multiply it by this number here, correct? Take this input, multiply it by this number here. Add them, you produce this output, correct? Yes? How is this output produced? Same thing, but this input, and this input, correct? Let me ask you, how is this output produced? So actually from the physics point of view, what is happening? It's this, and this coming together to produce this. But I don't have direct access to these numbers. I do have indirect access to these numbers. Where are they? I have them here. Correct? Right? And so what I am going to do is, well, that line is already there. That is one line. And then instead of taking this number times this multiplier, I am going to actually take this number. Okay. Instead of showing it to you like this, I am showing you like think of a wrap around universe which actually wraps around like this. Okay. So I am doing the same thing except my universe is actually wrapping around. Here you go. Do you see what I did? So it is this times that line, this times that line, and then this times this line, which produces this output. Do you understand this? So your gathering rule is gathering, and sometimes it has to go around the boundary of periodicity to gather the numbers. Okay. This specific way of performing a convolution has a name. It's called a circular convolution. For obvious reasons. It's going around in a circle. Okay? Write that. So what is a circular convolution? I imagine that instead of a blackboard, we have been provided like a drum. Okay. Imagine a drum shaped blackboard. Okay. And on these drums are those 8 numbers written. Okay. That's like a natural representation of periodicity because there is no boundary. It's just going around and around and around periodically. Okay. Those same numbers keep on happening one after the other. And on this drum, just like originally, if you imagine the flat blackboard and you have this vision in your mind of what a convolution looks like, the same rules keep on applying, the same spreading rules or the same gathering rules keep on applying. Now imagine the same kind of structure on the drum, that you have these numbers on the drum and you have a spreading rule and it's shift invariant, so the same numbers keep on applying, but these numbers are now going around and coming back. Okay? That is what is happening to produce certain output numbers. Either a spreading rule or a gathering rule. The gathering rule is going to still be a flip of the spreading rule. Okay? You can try and work this out yourself with examples on a simple sheet of paper. Try to do this. Okay? It's fun. So that's a circular convolution. As a matrix, let me put in some numbers here. Okay, let us say that I had the numbers 5, -1 and 2 are my multipliers. What will this matrix look like? So 5 -1, 2, okay, and 0, 0, 0, 0. What happens next? 0, 5 -1, 2, 0, 0, 0, right? And so forth. This is a matrix of the matrix representation of the circular convolution. Now let's be careful. What happens next? Sorry. I said and ended. 2, 0, 0, 0, 0, 0, 5 -1. What happens next? -1 goes up. -1, 5, 0. Sorry, Mayasa. Thanks. -1, 2, 0, 0, 0, 0, 0, 5. What happens next? But that's there. This is the matrix representation of the circular convolution. Does this make sense? 8 rows, 8 columns. Did we get that right? Yes. Nice. Okay. This is a Toeplitz matrix, but a Toeplitz matrix going around in a circle, which is called a circulant matrix. Write this technical term. You'll find it in textbooks. Circulant matrix. So, look at what is happening. How is, did you write this down? Okay. Now, how does it apply to this? What was it? 3 minus 2 minus 3 minus 2. Okay, whatever it is. 3 minus 2 minus 3 minus 2. 2 minus 1. 4, 1. Okay? And I ask you, how is the first output produced? The first output is produced using the first row of this matrix applying on this column, correct? Right? See if it's doing the right thing. Is it doing what we expect it to do? Because it picks up 5 from the top, and it picks up this 2 times and minus 1 times the other end. Okay? So not a transpose. Where does the flip occur? Where does the scatter gather flip occur? Here is where it occurs. The scatter is like this, 5 minus 1, 2. And the gather is like this, 2 minus 1, 5. Did you get it? The scatter gather flip is actually just, if you write numbers in this fashion and then you read them in this fashion, they end up being read in the opposite order. Nice, no? Yes.
We just transpose it and get the gathering matrix.
No, don't transpose anything. This is your linear operation. Don't transpose anything.
I'm not saying to transpose anything, but if we want for the gathering operation, the Toeplitz matrix will be.
It's the same. If you go for gathering, you write gathering rule on the row, which is the spreading rule on the column. It's the same thing.
Scattering and gathering are two viewpoints regarding the same operation. Okay? They are in matrix terminology, they are the viewpoints of what happens to one particular input versus how is one particular output generated. What happens to one particular input is present on particular columns. How one particular output is generated are rules written on rows. And so the scattering view is present in columns. The gathering view is present in rows. It's the same linear operation. No one's taking actual transposes of the matrix itself. Okay? Now, let's spend a little bit of a moment on the issue of, but what if I had more than 3 lines? Because that was a question that was presented, it's correct question. Right? I mean, who said I should have 3 lines? So general convolution, have many lines. 4 lines. What will happen if there are 4 lines?
What if there are more than 8 lines?
Correct. That's the real question, isn't it? 4 lines, they jumped the gun. 4 lines, I'll go 5 lines, 6 lines. See, that's what happens. No. What if there are more than 8 lines? What happens? Tell me what happens.
Like 5 times that plus 5 times that, so we can just add it, right? Yes.
Yeah.
Yeah. Okay.
Could you explain it in simple terms?
Yeah, I will. You see the issue? If there are up to 8 lines, it's okay if they are, bunched together. But what if there are 9 lines, for example? If there are 9 lines, then let's say one is going here and one is going all the way here. Okay? Okay? Do they have to have the same number? They do not. He's saying 5 plus 5, but they don't have to 5 and 5. Right? It could be 5 and 13. Such a strange number. Okay? It could be any number going here. Right? Because the convolution is still a convolution allowed to do anything. No one is saying the convolution is 8 periodic. Please understand this. The convolution is a straight convolution. This is actually very important to understand. The convolution rule is not periodic on its own. The input is periodic, hence the output is periodic. The same convolution rule applied to a 5 periodic input will produce a 5 periodic output. So the convolution is not periodic. Okay? So, now, if I had a line going here in the convolution and had a multiplier of 13, now what do I do? Yes, I just add that 13 and 5 and create a new number 18 coming from here. It's actually not. What is happening is 5 is coming from here and 13 is coming from there. But they are going to multiply the same number because my input is periodic. And which means that I can actually add the numbers together. I can add the multipliers together. So if the actual convolution has lots and lots of numbers, has 1,000 numbers, let us say, what do? I wrap around these 1,000 numbers on that same drum and I add all of them up to get only 8 numbers. Do you understand this? Formalize this yourself. There is a bit of effort in formalizing this. Okay? Because there is space for only 8 numbers here. Okay? So if you had lots and lots of numbers, they are all going to wrap around and produce only a circulant matrix of 8 numbers. Question.
Can we say that we are transforming a higher dimensional matrix into a lower dimensional matrix by taking the linear combinations of the columns of that higher dimensional matrix based on what you just did?
Yes. Yes.
The idea is kind of similar.
Yes. Yes. There are things like, yes. There are things like projections involved, and yes, something like what you just said is happening. Yes.
This will be problematic if signal terminated at some point.
If the signal terminated at some point, then
You take.
Then for boundary conditions, we need different matrix in some sense.
yeah, it's not a periodic signal, so this theory doesn't apply. So there's a terrible problem of what does this theory apply to. Now the unfortunate situation is going to the entire book. I showed you all these big books. They are all about circulant version of convolution. I'm saying this for the first time in lecture number 12, but the theory is all about circulant convolutions and circulant matrices and Fourier transforms actually on circulant. We'll see all of this happen. And so the question of but where does this apply is actually a real question. We will have some hand-wavy answers to it and some tricky answers to it and so forth in one next lecture. Okay. So, but what he pointed out is right. Your signal cannot end now. It's a periodic signal. It's not allowed to end. The only periodic signal having an end is the zeros signal. Okay. And now we ask, what are the eigenvectors of a circular convolution. Okay.
Any geometric progression will work. Any geometric progression that period. Like it can't go beyond the period.
What do you mean by a geometric progression that doesn't go beyond a period? Geometric progressions don't know to end.
Yeah, so we have a truncated geometric progression, which is periodic.
Like 139, 139. 139, 139.
Basically, that vector which we have written, that should be geometric progression.
Do you think that, like, let's take some geometric progression, like 1, 2, 4, 8, 16, 32, 64, 128. 8 numbers. It's a geometric progression. And where will it have to start? 1, 2, 4, right? 1, 2, 4, 8, 16, 32, 64, 128. 1, 2, 4, 8, 16, 32, 64, 128. 1, 2, 4, 8, 16, 32, 64, 128. Is this a periodic signal? Yes. Is this an eigenvector of a convolution? He's saying no. Why not?
I mean, you can, as a counterexample, take a convolution that shifts everything by 1 to the right. And if you calculate it, won't be.
You see that, right? Very clearly. If you take this, shift everything to the one right, that's a convolution. You are producing a periodic output. That periodic output is not a scale of the original thing. It's like doing something strange thing here. Okay? So this doesn't work. Okay. I know. I'll explain everything well at the end. This is like, yeah. The question is not well defined right now.
Could you at least explain the contradiction again and understand it properly?
Okay. I'll ask. Did you understand the issue? You understood the issue. Okay. Okay. The question we are asking is, are there eigenvectors of a circular convolution? Okay. One point of view is that the circular convolution is no new thing. It's just the original convolution, isn't it? Right? It's just these 3 numbers. Let's come back to 3 numbers. It's just these 3 numbers going like that. And any geometric series will be a eigenvector of that convolution. But any random geometric series that you take will not fit within the idea of being an 8 periodic signal. We want to restrict ourselves, the inputs and outputs both, to the space of 8 periodic signals. Yeah. Right? So we need to find something that is a geometric series in its entirety, as well as it is 8 periodic. Okay. And so this thing that I said, 1, 2, 4, 8, 16, 32, 64, 128, 1, 2, 4, 8. It's 8 periodic, but is it a geometric series in its entirety? No. That's why it's not working. You need something to be a geometric series from -infinity to infinity. but also need it to be 8 periodic. And what is one such geometric series? Like a simple one is 1i square I cube. What's the number after that? I fourth is just 1. 1i square I cube. And it comes back to 1. This can only happen with complex numbers. It is 4 periodic. And is something that's 4 periodic 8 periodic? It is. Okay. So here is what we find. Okay. Now pay attention. Here is something that is a geometric series that is also 8 periodic. 1 I square is what? Minus 1 minus I. 1 I minus 1 minus I. 1 I minus 1 minus I. Is it 8 periodic? Yes. In fact, it does 2 whole periods, but that's okay. As long as it comes back to itself 8 samples later, it is 8 periodic. We know this is a geometric series, right? Yes. It's one angle 90 degrees basically. It's a spiral which is turning 90 degrees every sample. Yes. So we know that it is an eigenvector because it's a geometric series. Every geometric series is an eigenvector. Every spiral is an eigenvector. We know all of that. Okay. It is also 8 periodic. And hence, we found an eigenvector. Sorry. Now, we found an eigenvector of this circulant matrix or this circular convolution. Okay. That's the eigenvector 1i minus 1 minus I, 1i minus 1 minus I. We know, just forget the circularity for a moment. We know that that spiral will produce an output spiral of the same turning speed, correct? Right? Which means it's going to be a screw of the same turning speed, but it could be bigger or smaller and it could be rotated. Will it still be 8 periodic? Yes, because it is the same turning speed. So it has to repeat after 9 samples. And the 9th sample has to be the same as the first sample. Okay. And so if you just look at it as an 8 vector, it has to be a scale of the input screw. Okay. And so we found one eigenvector. Now the question is, can we find enough eigenvectors? And we are going to discuss that after a break. We have found ourselves an eigenvector which is 8 periodic and a geometric series, an infinite geometric series. Okay? Isn't that cool? That is very cool. How many dimensions does this eigenvector span? One eigenvector can span only one dimension. What can it do, poor fellow? Right? An eigenvector and all its scales will span only one dimension. What does the geometry look like? All scales of this eigenvector. So straight line.
I mean,
The smaller
So signal-
dimensions
in the 4D play. No, 8.
In any dimension space, it will be a line.
the high dimension.
Okay. Listen carefully. We have this eigenvector 1 I minus 1 minus I, 1 I minus 1 minus I. Yeah, this eigenvector is fine. Visualize this. Keep it in your head. What are all its scales? They are its various amplifications as well as rotations. Huh? Remember, this is now happening in complex numbers. We silently moved into complex numbers because we were trying to find geometric series which are periodic. Unfortunately, there are almost no real geometric series which are periodic, so you have to go to complex geometric series. That's how we switch to complex numbers. This is where the complex numbers have come from. Okay. So what is the geometry of all scales of this eigenvector? A circle. Is it a circle? Circle is such a different answer from straight line. You are saying straight line and now you are saying circle. Is it true? Is it really a circle? Or a plane? Straight line, circle, plane. स्कूल में सिखाया सब बोलते थे कुछ तो होगा. Yes.
A plane,
Why?
because that will be the space spanned by the complex numbers.
How?
I mean, the scales are complex numbers, right? So the space spanned by all the scales, which are complex numbers, will be a plane, and that will be the space
Okay.
line.
Yes. Do you remember this? That what are all these scales of a complex vector? They are all the amplifications and rotations of the complex vector. And they form a plane in a high dimensional space. How do they form a plane? You have to remember this. The complex vector itself and its 90 degrees rotated version together form two perpendicular vectors in a high dimensional plane. And any other rotation and scale is a linear combination of these two. We did all of this in the skipping rope lecture. Okay? Remember that? And thus, all these scales and rotations together form a plane. So, the eigenvector we have found and its various scales and rotations form a plane. So, they span in geometric space a two-dimensional space. What is the dimensionality of this whole space though? How many geometric dimensions are there in this space? 16. 16. How come?
2 for each real and complex.
Real and imaginary, right? Each of these is now allowed to be a complex number, which means two geometric dimensions for every sample. And so we have 16 dimensions. Do you remember this? We studied this, that a k complex dimensional vector is a 2k geometric dimensional object. Okay? So in this 16 geometric dimensional space, we have found something that spans two geometric dimensions. How many such things, if I find, will I at least have a chance of spanning the entire space? 8 such things, if I found 8 such things, each spanning 2 dimensions, 2 geometric dimensions, then if I am able to show they are independent of each other, then I will have spanned this entire space using eigenvectors. So my job is now to find 8 such eigenvectors, which means I have to find 8 complex spirals or geometric series which are 8 periodic. I have found one, I have to find 8.
Constant one.
Oh, is that one of them? Just one. Is that a geometric series? Yeah. Is it 8 periodic? Yeah. So we found one of them. Okay, write down these things. We have to get to 8 of them. So okay. Yes, that's right. We'll go there. Okay. So one of them is 1, 1, 1, 1, 1, 1, 1, 1. Right? One of them is 1i minus 1 minus I, 1i minus 1 minus I. We have found 2. He's proposing a third one. 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Is that a geometric series? Yeah, multiply by minus 1 every time. Okay. Or you can think it's a spiral with a turn of 180 degrees. Okay. We'll come to that in a moment. That's a good point. So 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Write that down. We found a third one. Okay. Is it 8 periodic? Yes. It also has other periods. What other periods does this thing have? It's 2 periodic. It is 4 periodic. It is also 6 periodic. It's 8 periodic. It's also 10 periodic. It has other periods, but it has 8 periodicity, and that's fine for us. Okay. We found 3. There's a fourth claim here. I. Is that an eigenvector? It is an eigenvector. Is it a distinct eigenvector? No. Which one is it? It's 1, 1, 1, 1, 1, 1, 1, 1. It's just a scale of that. But it's like a turn scale, right? By the way, what he said about circles is not wrong. Huh? If you take any vector, forget eigenvector, if you take any vector and just see all turns of that vector, don't amplify, just turn them. What geometric object do you create in that high dimensional space? You actually create a circle. Actually create an exact circle. Okay, so the circle is there somewhere. Okay. So we have found 3. 1, 1, 1, 1, 1, 1, 1, 1. 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. 1i minus 1 minus I, 1i minus 1 minus I. We need 8. Come on. 5 more.
1 minus I minus 1 I.
1 minus I minus 1 I.
Right.
No.
Yes, no? 1 minus I minus 1 I. Right? 1 minus I minus 1 I minus I. 1 minus I minus 1 I. 1 minus I minus 1 I. Is that a geometric series? Yes, going minus 90 degrees. Right? Minus quarter turn per sample. It is a spiral. It is a geometric series. Okay. Is it 8 periodic? It is 8 periodic. What is the slight question we have in our mind? Is it a scale of 1i minus 1 minus I? Is it a scale of 1i minus 1 minus I? Doesn't seem to be. So let's write it down provisionally. We'll see what happens. So we have a fourth one. Okay. 1 minus I minus 1 minus. 1 minus I minus 1 I. Okay. Now, if you remember what we did in the previous lecture, this is going to be something useful. Why? Because it's actually the conjugate spiral of the 1i minus 1 minus I spiral. They're going around like this. And so the two together will actually form sinusoidals if we wanted them to form sinusoidals. And so they actually have distinct purposes, which means they are independent intuitively. Okay, so intuitively that's going to be a good choice actually. We will prove it in some time. Okay. So we have found 4. 4 more. Huh? 8th roots of unity. So propose something.
1 plus I by root 2.
Omega is 44.
1 minus I by
1 so 1 plus sorry 1 plus I by root 2 I not root 2.
So that's not 1 by root.
No, but pi by 4 also.
Pi by 4 we have written. No, we
Huh?
haven't.
No, pi by 4
We
would
need to do
be
pi.
Remember, a pi is half a turn. Two pi is a turn. Yes. So, simple thing is 1/8 of a turn. That's why turns are easy. This pi business and root 2 business is hard. 1/8 of a turn. Correct? 1 at an angle 1/8 of a turn. 1 at an angle 1/4 of a turn. 1 at an angle 3/8 of a turn. 1 at an angle half a turn. And 5, 6, 7. And you're back. Okay? So this. Find out the numbers on your own. Is that a spiral? Yeah. Is it 8 periodic? Yes. Comes back on the 9th sample. Question? By the way, our real numbers now go up and imaginary numbers go like this. Remember that. We made that change last lecture. So, this. Right? Okay? So, we found a 4th. Is that our 4th one? 5th one? Nice. Found 5th one. Let's reverse it. Going like this. Okay. Found a 6th one. 2 more to go. Do you understand this? This is, what is this spiral? 1 at an angle of 1 by 8. This is in turns now. 1 at an angle of 1 by 8. 1 at an angle of 2 by 8. 1 at an angle of 3 by 8. 4 by 8 and so forth. Okay. 2 more.
You pick every 4th point and then we repeat until we get all the points. I think.
Every 4th point?
4 or 4. Oh no, sorry. I meant 3rd.
It starts from 1.
You meant? 3rd. He guesses 3rd. Sorry. Is that what you meant? That's what you meant. Try it, see if it works.
Till now we have been in a sense doing this that way, skipping, taking every second, every third. So that is our algorithm.
That is the algorithm. Yes, you are right. Okay. Okay. Look at his proposal, and the algorithm is also very nice. I'll explain his algorithm in a minute. So, it's okay. We are making this much of a turn every sample. Okay. This much of a turn every sample. So, we make 3/8 of a turn every sample. Seems odd. But really the question is it a spiral? Yes, it's a spiral because we are turning. The question is, does it come back after 8 samples. Does it come back after 8 samples? How many turns does it make? 3 turns after 8 samples, and that's an integer number of turns, so it's back. As simple as that, right? And we can see it here, then here, then it goes 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 here, and we're back. Made 3 turns. Okay? And what is the last spiral we are looking for? The reverse of this one, which goes minus 3/8 of a turn per sample, and it will come back after 8 samples. Okay? And so the algorithm he is referring to is basically any multiple of 1/8 of a turn. Right? Let's not call it a scale. Any multiple of 1/8 of a turn is going to be a spiral that is going to be 8 periodic. So a spiral that makes 1/8 of a turn in a sample will make how many turns in 8 samples? 1 turn. A spiral that makes 2/8 of a turn in 1 sample makes how many turns in 8 samples? 2 turns, which is an integer number of turns, which means it's going to be back. And that was our spiral 1i minus 1 minus I. The spiral that makes 3/8 of a turns in a sample makes how many turns in 8 samples? 3 turns. And so it will be back. What's the next one? The spiral that makes 4/8 of a turn is actually what? Just the 1 minus 1 thing. Right? What's the next one? You can say the spiral that makes 5/8 of a turn, or the same thing you can call it the spiral that makes 3/8 of a turn, because the angle is the same. 5/8 of a turn and minus 3/8 of a turn are the same angle. Angles go around in a circle. Okay? Right? And so that's the next spiral. The spiral after that is what? This one, which is the 1 minus I minus 1i spiral. And the one after that is this fellow. This fellow. And then finally, you have the spiral which doesn't turn. Makes 0/8 of a turn per sample. So in 8 samples, how many turns does it make? 0 turns, which is an integer number of turns. Did we find our 8 spirals? Yes. So with these 8 spirals, we have a chance at least. We have a chance at least that we span the 16-dimensional space. Right? Now, once again, if we do span the 16-dimensional space, then these eigenvectors are an entire complete analysis of the convolution, because they will tell you what will happen to any input. Because any input, any 8 periodic input, will be decomposable into these spirals. Do you understand this? We have not proved this yet. We have not proved this yet. We have candidate 8 spirals. If we prove that, if we prove that they are independent of each other, then automatically they are going to span this space of 16 geometric dimensions. Sitting within that space, if you are interested in it, is the space of 8 periodic real signals. And so it will be a complete analysis of 8 periodic real signals. Okay? And I'm going to tell you what the analysis is. Okay. So here are your spirals, right? So this is like 1, 1, 1, 1, 1, 1, 1, 1 is one of your spirals. Then the next spiral is this 1, then it comes out of the board like this, okay? And then comes out of the board like this, and then goes here. Sorry. Here, okay? Did this, and then a faster one, and so forth, okay? So this is making 0 turns. This is making 1 turn in those 8 samples, 1 turn. The next one is making 2 turns. The next one is making 3 turns. The next one is making 4 turns, which is just 1 minus 1, 1 minus 1, and so forth, right? I'm going to ask you, what is the inner product of sum 2 of these? Okay? Right? 0.
I mean, they have to be. I'm guessing it's orthogonal.
They have to be zero.
What?
You're trying to prove their independence.
You seem very inspired by the fact that the papers will be served in a minute. So it has to be that way, right? Otherwise, how do you solve this?
I was thinking that each of them has a different frequency of emission. So they cannot be scaled for each other.
Yeah, but we are asking, yes. Independence is not that trivial either. Because you also have to prove that none of them is a linear combination of any of the others. But you can do something simpler, which we won't prove. But if you prove that all of them are orthogonal, so you are going in the right direction. If you prove all of them are orthogonal, then they have to be independent. So, okay, here's the proof. What is, simple thing. What is the inner product of this thing with itself? 8. Agreed? 8. Is this fine? Inner product of this thing with itself is 8. What is the inner product of this thing with itself? 8. Why? What is the inner product of a complex vector and a complex vector? Remember, you have to conjugate one of the complex vectors, right? So, if you take the inner product of this thing with itself, you are, while multiplying, you are actually taking the conjugate spiral, right? So, as the original spiral goes this way, its conjugate goes this way, where will the multiplication always come to? 1. The multiplication will always be plus 1, right? And 8 of them will give you the inner product of 8. Okay? Same thing will happen throughout. So, the inner product of any of these spirals with its own self is going to be 8. Write down this sentence. Okay? Now, let's calculate the inner product of this with this. What is that? 0. How come?
I mean, it's basically adding all the numbers by itself, and they kind of this symmetry. So this cancel that cancel.
Yeah. It is. So let's conjugate this fellow. We have to conjugate one of them. Okay. So let's conjugate this fellow. What is the conjugate of this? Its own self. Right. So these are all ones. And then this is just itself. And so basically you get these 8 numbers. Correct? As the multiplications. And you have to add them. What do they add to? 0. Correct? It's like 8 ants trying to take a piece of cheese to 8 different ant hills. My favorite example. So, and the cheese is not moving. Cheese is 0. Okay? So, what is the inner product of these two? It's 0. Similarly, inner product of this with anything is going to be 0. Correct? What about these two? Now you have to conjugate one of them. So let's conjugate this one. So look at what happens. You have one spiral, right? So the spirals we are trying to take inner product of is the spiral that is going to make 1 turn and the spiral that is going to make 2 turns, correct? You conjugate the one spiral, you get the -1 spiral. You take the multiplications, what happens? You have the multiplication of a 2 spiral with a -1 spiral, what do you get? You get the 1 spiral. Because this is going around at a speed of 2/8 per sample. This is going at a speed of -1/8 a sample. Their multiplication is actually going to average them out and go at a speed of 1/8 a sample. Because remember, multiplication is addition of angles. So if this is going around at a certain speed, this is going around at a certain speed, their angles will add, which means you get a spiral. And what will be the sum of that spiral? 0. Correct? If you don't understand this, work it out at home. It's a trivial argument actually. Going around at 1/8 of a sample, which means the sum is 0, which means that the inner product of these two is 0. Okay? So essentially what happens is as follows. As long as you take two distinct spirals, their inner product is always 0 because conjugating one and multiplying to the other always gives some other spiral. And whatever that spiral is, its sum is 0. The only spiral whose sum is not 0 is the 1-1-1 spiral. And the only way to get the 1-1-1 spiral by conjugating one and multiplying to another is to use the same spiral twice. That's the only way to get two of them to always add to 1-1-1-1. Okay? So their self inner product is 8 and their cross inner product is 0. Which means that these 8 complex vectors are all, each of them is spanning a plane and every plane is perpendicular to every other plane. By the way, this is something that we have no visualization of because this happens in at least 4 dimensions. 2 perpendicular planes, or let me call it 2 orthogonal planes just so that you understand what I am saying, is not visualizable. It's not this, okay? It's not this. Every vector in one plane is orthogonal to every vector in the other plane, which is a 4-dimensional object not visualizable to us. So actually what is happening is, these 8 spirals, each of them is spanning a space which is 2-dimensional and they are all orthogonal to each other, which means that together they span that 16-dimensional space. Okay? They're basically, you can think of them as 16 orthogonal vectors in the 16-dimensional space. What this means is that you can take any input vector and decompose it into those 8 spirals. Okay? Furthermore, it's very easy to decompose it into those 8 spirals. How will you decompose any signal into these 8 spiral signals? Absolutely, you will take the inner product. Why? But that's not enough. There's one another thing that you have to also say. Yes, but why is it enough to take the projection with each of those things? Because they are perpendicular to each other. Because these 8 vectors, these 8 spirals are perpendicular, orthogonal to each other, it is enough for decomposing a vector into those vectors for me to just take projections to each one of them independently. Why? Because the A transpose A part of the pseudo inverse is the identity. Does this make sense? We saw this in lecture number 3. U dot V term is 0. Okay? Go back and see that lecture. We are using entire lectures in seconds now. Is okay? Right? Basically, it's basically a graph paper. What is it? It's basically a graph paper. Right? You have this point. How will you describe this point on the graph paper? By dropping perpendiculars on axis of the graph paper. And why can you do that? Because the axes of the graph paper are themselves perpendicular to each other. That's all we are saying. But we are saying it in 16 dimensions. Okay? So this thing, we'll see the exact mathematics we have created next time. It's just the inner product actually. Just the inner product. Taking the inner product of any signal with respect to the 8 spirals will produce a decomposition of the signal into 8 spiral signals. Each of these spiral signals is going to suffer an eigenvalue, and you can reconstitute the eigenvalues at the output to produce the output signal. Okay? This decomposition into spirals is just a different graph paper put on top of the same 16-dimensional space. Do you understand this? It's just different planes. It's the same vector. It's the same vector. The vector is the same vector, but it is now measured on this basis rather than being measured on the original basis, which was 1 0 0 0 0 0 0 0 1 0 0 0 and those 8 things. That was the original basis. This is a different basis. The vector is the same. Okay? You are in the same kingdom, but you have a different map of the kingdom. You remember the story of the traveler? There's the traveler who traveled all around the world and came to what he thought was a wonderful new kingdom. Turned out it was the same kingdom, but it had a rotated map. That is what the Fourier transform is. It's just a literally rotated map. The rotation is happening in 16 dimensions, but it's literally just a rotated map of the original time domain signal. Okay? Rotated in such a way that the axes are eigenvectors. So that convolution, instead of being this very complicated operation, just becomes multiplications. That's it for today. We will see the exact mathematics of the Fourier. What we learned today is called the discrete Fourier transform. What we learned last time is called the discrete term Fourier transform. The periodic version of that is called the discrete Fourier transform, which is what we learned today. We'll see its exact mathematical formulation the next time. We almost have it. We just need to write it in mathematics. We'll see that next time, and then we'll see its applications. Thank you very much. See you next Thursday.